Hello, so welcome to this course, and as you all would know, this is a course on plasma physics uh, being taught in the January 2021 semester. Supposed to have started in January, of course, but unfortunately, because of the circumstances, it's only starting on February 8th, right? And what we will be doing in this course, the way this course will be presented, I will be, for those of you who have taken my previous courses, they know my style. Last semester was really the first semester I taught entirely online. And so what I'm going to do is do a mix of this kind of blackboard. This is the blackboard, this kind of blackboard kind of writing, and slides, okay? And I will put up all this material, including the recording, up on a Dropbox site that will be accessible to you. And so that's how it will go, right? So let's dive right in to the slides, and right. And I will be annotating on these slides as well. So this is a course in plasma physics. And why do we study plasmas? Because plasmas in various forms constitute over 95% of the observable universe. Okay, and I emphasize, the adjective observable. Okay, because that's what we're focusing on right now. And I need to figure out now how to write on this, and I'm not sure how. Okay, we'll figure that out uh, in due course. Highlighting is not what I want, but anyhow, so I want to actually be able to write on this, and I used to be able to do this earlier, but now I've forgotten how. Anyhow, let's go ahead. Right. So plasmas in various forms constitute about 95% of the observable universe, and by observable I mean baryonic matter, okay, not the exotic stuff like dark matter or even more exotic dark energy and things like that. That's not what I mean, right? So we're simply talking about regular baryonic matter, and it's a majority of stuff, and so it's essential to know what they are, right? So the first point here was by way of an astrophysical kind of motivation. The other point by way of the lab applications is that as you all know, nuclear fusion energy is the energy source of the future, as opposed to fission, which is already achievable as of now. But fusion is something that's still being pursued. I don't know how many of you have heard about ITER, the huge experiments that's being conducted by an international consortium. So it's all about plasma physics. Okay, so essentially what you're trying to do is you're trying to replicate the conditions at, roughly speaking, you're trying to replicate the conditions at the core of the sun. Okay, you're trying to derive energy by fusing hydrogen to helium, roughly speaking. Okay, and so the state of matter in which you're trying to do this is a plasma state of matter. Okay, so an understanding of plasma physics in the lab context is key to the important push towards harnessing energy from nuclear fusion. So there you go. So here's a lab plasma physics motivation, and there is an astrophysical plasma motivation. This is far too general or diffuse for you to have an immediate appreciation of that. But we will come to applications, as and when in due course. Okay, right. So yeah, I think right. This is where pencil. Oh yeah, right. Exactly. There you go. So now I can write here. So this would be, for instance, astrophysical plasmas. And these would be lab plasmas. And the basic physics underlying both of these is similar. There are differences, of course, but it's this course is all about just the basics. Okay, and as for all I want to say by listing out these things is that it will be the basics that you learn in this course will be useful for those who want to go on to do lab plasma physics as well as astrophysics, in particular astrophysics with a slight emphasis towards astrophysical plasmas. Okay, so this course will provide an overview of the theory of magnetohydrodynamics and plasma physics with a view to applications in astrophysics and the laboratory. As this is just repeating what I just said a minute ago, and we will explain these two words, magnetohydrodynamics and plasma physics, as we go along. I prefer to simply call it plasma physics. They're both, part of this. This is more of a fluid treatment, and this is more of a not a particle treatment, but a distribution function kind of treatment, plasma physics. We will see all these as we go along. Okay, so this is, I just want to emphasize that although we will go into some detail, this is really just a basics kind of course, just to establish the basic phenomena. That's all we'll be doing in this course. I will be touching upon applications as and when permissible, but just want to alert you to the fact that there's a lot more out there than what I can possibly cover in a course like this. Okay, so as far as prerequisites, you need to be strong in your basic electrodynamics. You need to, for instance, Maxwell's equations by way of electrodynamics. I would say that things like, by way of electrodynamics, you should be very familiar with Maxwell's equations, obviously, waves. That's about it, really. You need to be you need to know these things. I mean, I will not have time to revise these things. Okay, propagation phenomena, wave propagation. Okay, so these kinds of things you really need to be very familiar with. Okay, the other thing that the other prerequisite I would know, I would require is at least some familiarity with kinetic theory and some statistical mechanics. By kinetic theory, I really mean gas kinetic theory. Okay. And I don't mean any great detail. For instance, I would expect you to know things like RMS velocity, right? Where does it come from? Distribution functions, right? E.g., the Maxwell-Boltzmann, pardon my handwriting, the Maxwell-Boltzmann distribution, right? These kinds of things I want you to be thoroughly familiar with. And how, from the distribution functions, how you get moments such as the velocity, pressure, density, things like this. Okay, so I want you to be very familiar with this. Oh, what did I minimize now? Right. And some familiarity with continuum or fluid dynamics is helpful, but not essential. But I would strongly urge you to for those of you who already taken the fluids course, that's good, well and good. You don't need to do anything more. Perhaps just revise a little bit. For those of you who you have not, it's okay. you can take this course as long as you are responsible for so essentially some basic background in fluids you will be responsible for this. Okay, as long as you're willing to pick up this this is fine. You can go ahead and take this course. Okay, and what do I mean by basic background? Things like mass conservation, mass, momentum, and to some extent energy conservation, in fluids. Not for discrete particles, but in fluids. Okay, you should know, for instance, the mass conservation equation that looks like d rho dt plus divergence of rho v equals 0. You should know that this is the mass conservation equation. You should know something about the Euler equation. At least have some idea of the Navier-Stokes equation. Okay, and all of these things I will be putting up. Background. I'll be putting up material on the course website, and you just look up these kinds of topics in those books, or just pick your favorite book and learn this by yourself. The other thing I did not emphasize, I did not mention by way of prerequisites, is that you need a strong background, and you would need this in any case in order to understand fluids in basic vector calculus. Okay, for instance, gradient, divergence, curl, things like this. You should know these intimately. Okay, also some familiarity with tensors. Okay, so these are the sort of the basic background that I would need from you. I will put up the lecture notes also on the website, and you can take a look. You can quickly thumb through the lecture notes and see what's in there. That'll also give you an idea of what's expected in this, of the kind of background that's expected in the course. Okay, so I strongly urge you to think about what's needed, and then decide whether you want to take the course or not. Because we will be, even though we will only be covering the basics, we will need to move fairly fast through the course. Okay, all right, good. Now, course texts. I would say that these two will be the primary course texts. A book on plasma physics by Sturrock, and then a book by Boyd and Sanderson. I will put up all of these on the course webpage, and the book by Arnab Raichaudhuri on plasma physics and physics of fluids. I had followed some of this. I like this book. I followed it to some extent in my fluids class as well, and also some informal notes on fluids, and actually fluids and magnetohydrodynamics, I must say, by Jean Eilich. I find these notes really nice, and also some notes on magnetohydrodynamics by Sprout. So these are informal notes that I found here and there, and I grab them and I save them. I find them very, very useful, and I will also all of this stuff I will put up on the course webpage. Now, one very important thing, I will keep these notes for the entire course, no problem, because these don't really have copyrights or anything. These are informal notes, whereas these are, ebooks that we had a subscription to in the library, but I'm not sure whether we still have them or not, but I downloaded them legally. But I will take this off. I will take off these 3 books in a week or 2. So I urge you to download them and keep them, after which I will not keep them on the course website for the remainder of the course. Okay, so these are the course texts, and as I always used to repeatedly emphasize in the fluids course, you will have access to these slides that I'm using, but please do not confine yourself just to the slides. Okay, it's very, very important that, what the material that I'm using in the slides are simply taken from one of these sources. Sometimes from elsewhere, but mostly I confine myself to some of these sources. Okay, and I will try my best to sort of tell you where and which chapter and whatever I'm taking the material from. But it's really up to you to go back to the original sources and read. Sometimes, you might like the treatment in one book and not in another. That's fine, no problem. But please do read the books and go through things in detail. Please do not rely just on these notes and these lectures. It's very, very important. Right. Okay, so I have divided this course into 3 modules, or is it 4 modules? I don't recall now, but at any rate, right now we are only concerned with the beginning of the course, and the beginning of the course, I called it Module 1, and what we will do is essentially repeat a little bit, repeat the initial statement that I made, say a little more about the relevance of plasma physics in thermonuclear fusion, which as you know is the major which holds out major promise of clean energy in the future, and we will outline a little bit about plasmas in space. Okay, so after this, we will after this sort of introduction, we will plunge into the actual material of the course, and we will start talking about basic characteristics of plasmas. We will talk about collisions, collective effects, Debye shielding, plasma parameters, so on and so forth, and most of it is to be found in Chapter 2 of Starrock and Chapter 1 of Boyd and Sanderson. Okay, and then we will go on to orbit theory. Now, let me say something at this point. The first half of the course, or rather, let me say something about the second half of the course first. Okay, the second half of the course we'll treat a fluid comprising charged particles. Now, for those of you who have taken the fluids course, you know that there are no particles in a fluid. Lots and lots and lots of particles. When kind of coarse grained, right? You have tons and tons and tons of particles. Okay, and when there are so many particles in a some representative macroscopic volume like this, you can no longer make out the particle nature. Okay, it looks like a fuzz to you. It looks like there's just so many particles that you cannot, the individual particle, nature is not really evident to you. It's only when you go very close to it with a microscope that you can figure out the particle, that you can make out the motions of the individual particles. But that's not what we will be doing in the second half of the course. Okay, what we will be doing is looking at this thing from far away, a fuzzy kind of a thing, so that you'll be only concerned with the collective, the behavior of the mean, so sort of a mean nature. Okay, a mean description of all these particles. You'll be concerned with the average density of particles here. You'll be concerned with the average velocity of all the particles. In other words, you'll be concerned with fluid phenomena.